that have the same number of protons but a different number of neutrons. So remember that the protons and, oops, that should say neutrons. The protons and the neutrons are in the nucleus of the cell, and then the electrons orbits the outside. And so when we talk about carbon, carbon has 6 protons, and so generally it is in the form of carbon-12, right? So sometimes we write it as something that looks like carbon, oh, the stupid pen, carbon-12, right? So this means that it has, its molecular mass is 12. So that means it has 6 protons and 6 neutrons. But sometimes you hear about carbon-14, right? So these are what are referred to as isotopes of carbon. They have the same atomic number, so they have the same number of protons, but they have a different number of neutrons. So for example, carbon-12 would have 6 protons, and how many neutrons would it have? Nope, carbon-14, excuse me, carbon-14, 8. Sorry. Carbon-14 has 6 protons and 8 neutrons, and so that's what adds up to the 14, right? This is actually produced in our atmosphere, and we take in some forms of carbon-14, and then when we die, the carbon-14 starts to get converted back to other elements. And so they use carbon-14 specifically for dating of fossils and dating of organisms that, the remains of organisms. So you can kind of determine how long ago an organism died by how much carbon-14 is still left in it. So these isotopes, right, so a characteristic of isotope is that they are unstable. So they undergo decay. So they will decay over time. And the rate at which they decay, you might have talked about this a little bit in math, because people in math like to use this example, is called its half-life. So that's like the amount of time it takes for half of the carbon atoms to be converted into something else, right? They decay over time, and as they decay, they emit energy. And sometimes this energy can be very bad, right? So we have isotopes of uranium. That can be mined, and they are radioactive. And what radioactivity does to our molecules, specifically to our DNA, is it causes the DNA to mutate. And so this causes the cells to not be able to function because their genetic material has been damaged. And so one of the signs of it, probably seen on TV, like in the shows, right, where people will get, you know, poisoned with radioactive plutonium or whatever, and their hair will start to fall out, and then they'll have just so many hours or so many days left before they die, because this leads to radiation sickness, right? So this is radiation sickness. Right. So sometimes they use these in the military, you know, weaponry that has radioactivity in it. And we also use radioactivity in nuclear power plants. Unfortunately, sometimes those nuclear power plants malfunction or get damaged, and they release radioactive elements into the atmosphere. Okay, or into the water. So one of the things about isotopes is that they can be used medicinally. And so here's an example of a isotope of hydrogen. So we can talk about hydrogen isotopes. Okay. So normally the most stable form of hydrogen and what it is most, like is this one right here. So it has one proton and it's called protium, right? And that means that is the normal, right, has one proton and one electron. So that's what we have in our bodies. But we can also produce what is sometimes referred to as heavy hydrogen. So deuterium and tritium are isotopes. Deuterium, deut means two, and so that means that there would be two subatomic particles in the nucleus, so they have a one proton and one neutron. And tritium means three, so that means that they have one proton and two neutrons. Okay? So protium is one, deuterium is another, and tritium is another. These are unstable, and so they will tend to emit energy. And so let's say we wanted to follow a chemical reaction in the body and see where the atoms go in the chemical reaction. Sometimes we will use isotopes of hydrogen, like deuterium, and we'll put them in a biological system, like a person's body or an animal's body. And then we would watch where that energy goes. And so that tells us, like, if we give them, sometimes this is given in the forms of like what is called heavy water. So if heavy water, instead of the normal hydrogen, has deuterium in it, then we can follow where that water molecule goes in your body and what it interacts with. Right? And so they are used medicinally to kind of determine how, what atoms do and how they travel. So there are some other examples of isotopes in medicine. Let's see what I have down here. Oh, this one's interesting. So this is, you probably remember these and maybe even have one, but these clocks that will glow in the dark, right? And so this clock, instead of the normal hydrogen, it has tritium. And so the tritium illuminates the face of the clock. And so it's not electricity that's letting it glow, but rather it is nuclear energy that is allowing that clock to glow. Okay, so if we look at the medicinal use of isotopes, sometimes we use iodine. So radioactive iodine. And again, if you go to the hospital, this would be under the purview of nuclear medicine. Okay. So you see a sign that says like radiology, and then you see a sign that says nuclear medicine, and that's what they're talking about. So does anybody know what gland in our body uses iodine? We might be able to look at using radioactive iodine, the movement of iodine through that gland. What gland in our body uses iodine? Anybody know? Thyroid. So our thyroid gland is located in our throat region. And if you don't have iodine, the thyroid gland will start to swell. And that's because it's producing a protein, but that protein has to be combined with iodine in order to release the hormone. So the thyroid produces a hormone that actually helps to regulate our metabolic rate. And so sometimes you see children or adults and they have this big, enlarged thyroid gland, and that is called a goiter. So lack of iodine, you develop a goiter. And if you give a person iodine when they have this symptom, then they can produce the hormone and the swelling of the thyroid gland will go down. Sometimes radioactive iodine is used to destroy the thyroid gland. So for example, if you have hyperthyroidism, this means that you have you're producing too much hormone, and this is sometimes referred to as Graves' disease. And it's relatively common. You have a high metabolic rate, which means that you're just burning energy really, really fast. And so you tend to get really skinny. So you get skinny and you lose weight. And another sign of a person who has hyperthyroidism is that they have bulging eyeballs. So their eyeballs tend to bulge out. I think it has to do with the fat, losing fat around their eye. So they look like they're like big eyes, right? And they're skinny. And so one of the things, this is actually quite common in cats. You have a cat. I had a cat once that had hyperthyroidism. And one way that you can treat it is you could go and you could remove the thyroid gland. But another way that you could treat it is you could give them radioactive iodine, and the radioactivity goes into the thyroid and it gets stored there and actually damage the thyroid so that it no longer functions properly. So you can treat it with radioactivity, right? And sometimes we do that with cancer too. We use radiation to get rid of the tumor. And so this can be treated with radioactive iodine. Oops, didn't do that. Dang it. Okay. Another interesting thing about the iodine is that sometimes we do not have enough of it in our diet. And so what in our diet has been iodinized? So what in our diet do we eat that has had iodine added to it? Salts, right? So you have what is called iodinized salts. Well, I'm talking about what in our food has been added. So like we add vitamin D to milk, right? We add iodine to salt. And so sometimes you get sea salt, and sea salt has not been iodinized. And so this is just to ensure that everybody has enough iodine. And it's kind of interesting because when the Fukushima and the nuclear power plants erupted, it actually released radioactive iodine into the environment. And so one of the ways that they were treating people and to try to protect them from the radioactive iodine is they were giving them iodine pills. And so they were giving them iodine pills so that their thyroid gland would store a lot of iodine and would not accumulate the radioactive iodine that they were taking in their bodies in water or in breathing it in. And so that is kind of another interesting aside about the radioactivity iodine. Okay, so there's other elements that are also used. And as I said before, iodine or isotopes emit energy, right? So if we're looking and we're trying to figure out where in your body is storing a particular substance, we can then inject your body with it, or they can inject your body with it, and then they can look to see where that energy goes, right? So where in that body. So if this was radioactive iodine, it would go to the thyroid, right? I'm not sure what this actually is. This is a diagram from your book, but that thyroid should light up if you have radioactive iodine in you. Okay, so that's the use of isotopes and how isotopes are a little bit different from elements because they are a different form of them that are less stable than the elements that we see in the periodic table. So those elements are in their most stable form and don't tend to emit energy in the terms of like gamma rays, gamma ray energy. Okay, so we talked about the different atoms and how they are characterized by the number of protons in their outer shell. Okay? And remember that the first shell only stores 2 electrons, but each subsequent shell stores how many? 8. So look at this one. This one, does anybody know what this one is? What's Ne? Does anybody know? What lights up our signs? Neon, right? So neon, right? So this has 1, 2, 3, 4, 5, 6, 7, 8. So it would be inert. It is not reactive. So we don't see neon as an element in our organic molecules. Okay, so in your notes, we were talking about molecular bonds. And we were talking about the elements that share electrons in order to fulfill the outer shell's requirements. And so I drew a picture of oxygen with 2 solid lines between it. And so here you can see that they're sharing 2 sets of electrons. And so if we counted that, that would mean that 1, 2, 3, 4, 5, 7, 8. Yeah. So if you counted 2 more, there should be 8, right? But there's only 6 in the outer one. I'm not sure that. Okay, so this is what is referred to as oxygen gas, right? So this would be another way to write it. And we mentioned that they're sharing the electrons equally. And so this is an example of polar or non-polar bond. Is it polar or is it a non-polar bond? Non-polar, right? Because they're sharing them equally. So if they're not sharing them equally, then it's said to be polar. So think about polarized. Think about like if you walk into a room that's polarized, you know, you have some people think of one thing and some people think of the other, right? If it's non-polar, then everybody's right the same, right? So it's sharing the electrons the same. Okay. So in the example of water, we see here that the oxygen would be stronger. So it's going to draw the electrons closer to itself, right? And so it's going to share these electrons unequally. So when we look at water, H2O, you should have this in your notes. This is an example of a polar covalent molecule. That's a polar, that's an A. This is a polar covalent molecule. So that's one type of bond, the covalent bond, where we have sharing of electrons. We have another type of bond, which is referred to as ionic. Okay. So ionic, rather than sharing the electrons, we have the actual exchange of electrons. Between atoms. And the best example of this is sodium and chloride. Okay. These are charged elements, and so we say that these are examples of ions because they're charged, right? If it has a positive charge, it's said to be a cation. So sodium is actually a cation because it has a positive charge. And chloride is an anion. So the negative charge equals an anion. Okay, but they're both examples of ions. So which one has an extra electron, the sodium or the chloride? Chloride, right? Because it has an extra electron because it has a negative charge. So when we look at this, we can see that these can form kind of a bond because of that exchange of electrons, right? So this is the ionic bond. So opposites attract. So this is an example of an ionic bond because the sodium has given up the electron and the chloride has received the electron. Now this bond is formed and it actually releases quite a bit of energy when the electrons move from the sodium to the chloride. So if we look at elemental sodium, elemental. Elemental sodium is something you wouldn't want to touch because it is highly reactive, and it is a solid, and it is metallic. Oops, metallic, that's an I. And then if you look at elemental chlorine, this is a gas, and it is yellow, and it's something you would not want to breathe. Chlorine gas would be really bad to breathe, right? So when you put those things together, they produce a chemical reaction that releases energy. We'll talk about exothermic, but it releases energy, and we get from it a substance that is very familiar to us, which is table salt. Okay, so sodium chloride, right? Sodium chloride. This is white, and it's granular, okay? And it is table salt. So by combining them, you change fundamentally their structure and then whether or not they're going to be reactive, right? So you never would touch elemental sodium with your hands, and you would never breathe chlorine gas, but we ingest sodium chloride all the time. So if we look at some pictures of these, right? So this is what elemental sodium looks like, and this is what elemental chloride looks like. And then combining those, right, is a chemical reaction that is releases energy, and it looks like that, right? So it's like, okay. And then the product of that is table salt. And that energy release has to do with the movement of the electrons. So if we look at this exchange of electrons, notice elemental sodium has an electron it was wanting to get rid of. The chlorine has 7 electrons in its outer shell, so it's wanting to get an electron. And so here, notice that that outer electron has just been transferred to the chlorine. The sodium is now happy and it's stable, and the chlorine is very stable, and then you get a structure that looks like this, right? And so that's the table salt. Okay, so that's different than the covalent bonds. That's an example of an ionic bond. Okay, the last type of bond that we're going to talk about are hydrogen bonds. And if you have taken chemistry, this is different than what they describe in chemistry. Okay, so I'm going to put different than in chemistry class. So this was always confusing to my students who were taking chemistry at the same time. They would say, that's not what my chemistry teacher taught me, right? Different than chemistry class. So hydrogen bonds are weak attractions between oppositely charged molecules. And they're designated using a dotted line. Not a solid line. So covalent molecules are solid lines, okay? So for example, if I was to draw my water molecule, okay, is this bond that I'm pointing to right here, is that a hydrogen bond? If you're in chemistry, you would say that's a hydrogen bond, but it is not a hydrogen bond in biology, right? So that is a covalent bond, not a hydrogen bond, not a hydrogen bond. That's just a scribble, okay? This is hydrogen. Okay. However, if you put 2 water molecules together, right, This is a negative charge because it is pulling electrons to it. This is a positive charge because it's getting its electrons pulled away. And so I can draw a dotted line between this, right? And so that is my hydrogen bonds. I'll put, this is my hydrogen bond. Okay. So this is the forces, this being attracted is the forces that keep water primarily in a liquid state on our planet, right? Water, it takes a lot of energy to break the hydrogen bonds. And so when you go from a liquid water to a steam, right? So liquid water plus energy could be the form of your like your boiling water, right? And then you produce steam. Okay. You are breaking not the covalent bonds, but you are breaking the hydrogen bonds, right? So hydrogen bonds are broken. But it takes a lot of energy to break those hydrogen bonds, right? So if you think about the ocean, solar energy can cause evaporation of the water, but most of the water is in the form of liquid. It doesn't evaporate really quickly like alcohol does. If you think about, you know, in your bathroom, if you leave the alcohol, the lid of the alcohol bottle off, you know, your kids do, and it's like 2 days later you come back and there's no alcohol, right? Because it evaporates really readily. So you're not breaking the covalent bonds. So steam is just this molecule, right? So that's just kind of floating around in the atmosphere. Clouds have those water molecules in them. And then when they condense into rain, that's the reformation of those hydrogen bonds. Okay? So the water condenses and forms rain, water droplets, and then falls back to the land. Okay. So what I'm saying here is that hydrogen bonds are the weakest bonds. They're not only found in water, but they're also found in the attraction of the different parts of a protein. So the reason why proteins fold is because of hydrogen bonds. If you're familiar with the structure of the DNA molecule, the reason why there's 2 strands of DNA molecule held together is that they're held together by hydrogen bonds. And so hydrogen, whenever you see a hydrogen bond, you know that at some point that hydrogen bond is broken, because it needs to be weak enough that you can break it to change the way that the molecule exists. Okay, and it's between 2 oppositely charged molecules. Okay, any questions about covalent, ionic, and hydrogen bonds? Remember that it's only the covalent where we see polar and nonpolar. So only in covalent do you have, you know, do you have to designate whether it is a polar covalent or a non-polar covalent bond. So in your book, they have the diagram here. Water molecules bonded together. Okay, so next we're going to talk a little bit about energy. And so energy is defined as the ability to do work. We can also distinguish between whether or not the energy is stored or whether it is being used at the given period of time. And so we can talk about kinetic energy. So kinetic energy is doing work. Right? The opposite of kinetic is potential energy. Right? And potential energy is stored. Okay? So it is not doing work at the moment. Okay. So we're going to talk more about this, but ATP is stored energy. ATP can be broken down into ADP plus a P. And ATP, I'll write what that stands for here. Adenosine triphosphate. So adenosine is kind of like the building block, and it has 3 phosphate atoms molecularly, covalently bonded to one another. So we can write it as, if I wanted to kind of write what it looks like, oops, adenine, and then I would have a phosphate, a phosphate, a phosphate. Okay. This ADP stands for adenine diphosphate. Plus a phosphate. Okay, so what this means is that now there's only 2 phosphate groups attached. That's 2 P's. Plus AP. Okay. So we have removed one of the phosphate groups, right? And when we remove the phosphate group, that changes the electron orbits, right? And the electrons come back towards the adenine, and that releases energy. And so then we have, this is the release of energy. Okay. So this could power molecular movements. So it could power pumping substances into the cell or out of the cell. It could also power muscular contraction, this energy. And so I would say that this is potential energy because it's stored, and we can store it in our muscles. So our muscles store lots of ATP, and then when the ATP gets converted, then it turns into kinetic energy. So this is chemical energy. And this would be, if it's movement, it would be mechanical energy. So chemical energy is the type of energy that is stored in chemical bonds. So I think I mentioned this before, but when you take propane and you burn it, you produce like light on your grill, and you also produce heat to cook your food. And so that would, propane has stored chemical energy, and then when I light it on fire and I burn it, it's turned into heat, right, and light. And so that's the conversion of chemical, okay, or into light and heat. But all chemical reactions are inefficient. And so what we see here is that when we convert from one form of energy to another, we lose energy as heat. Okay, so that's an arrow. Okay, so when I am exercising, I release energy as, I move my muscles, but I also release energy as heat. I get hot and I start to sweat and I start to evaporate water off the surface of my body. Okay. Okay, so that's some types of energy, chemical and mechanical. We also have what is called electromagnetic energy. And one form of electromagnetic energy that you can feel is sunlight. So you can kind of see it, and you can also feel it, right? So this would be sunlight. So this is different. It's not chemical. Sunlight's not chemical energy, and it's not mechanical energy. It's electromagnetic energy. And this is what actually plants use to grow. But there is a vitamin that we actually need in our bodies that we actually can use sunlight to produce. And what vitamin is that? Does anybody know? Vitamin D, right? So we can take cholesterol in our skin and we can convert it to vitamin D. And we can do that with sunlight. Okay. So if we don't get enough sunlight, how do we get vitamin D now? How do we supplement our food? I think I mentioned this already. Milk, right? So they put vitamin D in milk because vitamin D is necessary for calcium absorption. So there's calcium in the milk. If I don't have vitamin D in my body, I am not going to absorb it. So why not put the vitamin D right in with the milk so I can absorb it? So lack of vitamin D causes deformation in the bones. And so babies and children are especially prone to developing what is called rickets, where their bones are soft and you get the bow-legged, you know, the weird shaped skeleton because they don't have enough calcium because they're deficient in vitamin D. Okay, so the other thing that we need to talk about is our chemical reactions. And so I've been drawing chemical reactions already, but we want to talk about the different types of chemical reactions and what helps to speed up or decrease chemical reactions. So when we look at chemical reactions, we can have what is referred to as, I think we already talked about this, anabolism. And is anabolism building or breaking down? Building, right? So we can take A plus B, put a capital B there, and that would give us AB, okay? This is also referred to as synthesis, because I'm making something, I'm synthesizing protein, for example. So it's called synthesis, okay? Catabolism is breaking it apart. Okay. So here AB is broken down into A and B, right? This is also referred to as decomposition. So I'm decomposing it, I'm breaking it down, I'm breaking it apart. Okay. We can also talk about replacement. So this would be like if you had A and C plus B, right? And that gave you A plus CB. I don't know why I put C instead of B. I mean, C in front of B, but I did. Okay. So A was bound to C, right? And then it just got converted. So A is now, or C is now bound to B instead of A. So sometimes we'll see those types of chemical reactions occurring in the body. So we can talk about the speed of reaction. And so there are some things that speed up chemical reactions. And these in general, we'll talk about the rate of chemical reactions. There we go. So this is the speed, the rate of chemical reactions. So speed. Okay. Temperature is something that influences chemical reactions. What temperature is molecular movement. So if like I was to heat up this table, the reason why it'll feel warm to me is that the molecules are moving more rapidly. If you cool something down, you slow down the molecular movement, right? And so it's kind of interesting, in old panes of glass in houses, the molecules are actually still moving. The silica molecules are actually still moving in the glass. And sometimes you'll actually see the glass gets warped, right? So at the bottom, it actually kind of gets weird looking, like warpy. And that's because there's still movement of those atoms, right, in the pane of glass. And they're actually kind of flowing down, right, real slow. So molecular movement is, if we increase molecular movement, we increase temperature. So in general, if we increase temperature, we tend to increase the rate of reaction. up till a point. So sometimes temperatures can influence the actual molecules and decrease the rate of reaction. But if we increase the temperature a little bit, we're going to get an increase in the rate of reaction. Okay. We can also talk about the concentration of the reactants. And so if we increase the concentration, we're going to increase the rate of reaction. They're going to be moving around. They're more likely to come in contact with one another. And so the chemical reaction is more likely to occur. The other thing that really greatly influences chemical reactions in our body is the presence of enzymes. So enzymes are molecules that catalyze chemical reactions. And some chemical reactions do not occur at all unless the enzyme is present. So that says catalyze, that's a Z, catalyze chemical reactions. Okay. So for example, we have starch. If we took in starch, like a starchy vegetable, and we held it in our mouth, starch will get converted to a simple sugar called maltose. Okay. And the chemical that does this, that converts this, is an enzyme, and it is called salivary amylase. So it's really important. Anytime you see this ACE ending, this means that it's an enzyme. However, there are some enzymes that don't have the ACE ending. So it's kind of like, if it has the ACE ending, it has to be an enzyme. But it could be an enzyme if it doesn't. So like pepsin is an enzyme that we have in our belly that breaks down protein, and it doesn't have the ACE ending. Okay? But every time you see that ACE, you know that that is the enzyme. Okay. Okay, so what happens is that the enzymes can influence the rate of reaction, and enzymes do this by binding to the substrates. So enzymes have substrate binding sites. I'll show you a picture of this in a second. Enzymes are generally proteins, and they're have a really complex three-dimensional structure, and so they have little sites on them that bind the reactants. Okay, so we'll put that bind reactants. Okay, so we have the reactants, and they produce the product. Okay, so starch would be the reactant, the product would be maltose. The important thing to realize about enzymes is that they are not used up. Okay, so I'll put enzymes are not used up in the chemical reaction. They're not broken down. So they can actually bind, and they could actually cause the reaction to occur, then they release the product, and then they just go bind some more reactants, release the product. So they can actually be used over and over and over again in the system. And they do this by they tend to decrease, enzymes do, they decrease what is called the energy of activation. And that's the energy that is necessary for the chemical reaction to occur. So that says activation, active, IV, activation. So they decrease the energy of activation. Okay. So if we look at example of this, right? So these are my reactants. So this is a picture from your book. And this is the energy that is required, and it could be in the form of heat. So like, okay, it's warmed up, the chemical reaction is going to occur. But if I have an enzyme, then the amount of energy it takes to get those two reactants together to form the product decreases, right? And if we look at the enzyme, oops, I don't have a picture of the enzyme. Okay, so if you looked at the enzyme would actually have binding sites on it. I think there's pictures in your book, but binding sites that would bind the reactants and release the product. Okay, so last thing we're gonna talk about is water, and we're gonna talk about pH, because this is part of what we're gonna be doing in lab today. Now, water is really interesting because it actually exists in two different forms. It's really interesting for a variety of reasons. But this double arrow means that the chemical reaction occurs in two directions. So it releases hydrogen ions and hydroxyl ions. So these are called hydrogen ions. Would that be a cation or an anion? Cation, because it's positive. These are called hydroxyl ions. And those would be examples of anions because they are negative. Okay. So water actually exists in these two states. Okay. It just kind of goes back and forth, and it kind of equilibrates. Now, these two states are the basis for some characteristics of solutions that are distinguished as being either basic or acidic. Okay, so let's talk about acids. Okay, so acids are substances in solution that release hydrogen ions. Okay, so they actually increase the concentration of hydrogen ions. So a good example of this is HCl. So HCl can be converted to hydrogen and chloride. Right? So that's my hydrogen ion. It's released into solution. So hydrochloric acid is what we have in our guts, in our stomach, and it helps to break down proteins, and it helps to kill microbes. And it is an acid because when you put HCl in water, it releases hydrogen and it increases the hydrogen ion concentration. We can also talk about bases. So a base is a substance, I'll just put in solution, that removes hydrogen ions. So one that you might have in your kitchen is what is called sodium hydroxide. So this is, oops. Okay, so this is called sodium hydroxide. And so this is baking soda. Okay. And so if you put this in water, what's going to happen is that the sodium is going to disassociate, and then the hydroxyl ions are also going to disassociate. So they break apart, right? So sodium should have a positive here. Sodium. Okay. So you're like, well, how does that remove hydrogen ions? Well, that is actually going to cause that first chemical reaction with water to go the opposite way. So notice how this chemical reaction is going in both directions. But if I increase this one right here, If I increase the amount of hydroxyl ions, then more is going to react with the hydrogen and it's going to form water. So this it removes, right? It removes it because OH combines with H to form water. Okay, so that removes the hydrogen ions. Okay, so when we are measuring the acidity or the alkalinity, okay, we sometimes refer to the pH. Okay, so the pH is a measure of the concentration of ions, of hydrogen ions in solution. Okay, and it has a scale. It's from 0 to 14. Pure water, so that would be distilled water, which we're going to use today in lab. Distilled water has a pH equal to 7, and this is what we call neutral. Okay. Now the confusion comes in because the lower the pH, the more acidic a substance is, and so the higher the concentration of hydrogen ions, right? So if we have from 0 to 7, this is acidic, and I'll explain why in a second. And then 7 to 14, this is basic, and this is also called alkaline. So sometimes people who live in deserts have funny tasting water, and that's because their water is alkaline. It's got minerals in it that makes it more basic than what we generally use drinking. Okay. Okay, so why is it, if this is the measure of concentration ions in solution, why isn't it the higher the number, the greater the acidity? And it's because it's a negative inverse reaction. So if we look at the pH, and let's say we have a pH of 2 versus a pH of 4. Which one's more acidic? 2 or 4? 2. Which one has a higher concentration of hydrogen ions? 2, right? Because the concentration of hydrogen ions is 1 times 10 to the negative n, right? With n being this, right? So it's a log, because this is times 10, but it also is a negative log. So if I look at this one, this is, if I go 1 times 10 to the negative 2, if you remember your math, right? This means that I move the decimal places 2 places right here. So it's actually, this is actually 0.01. Okay. 1 times 10 to the negative 4th, right? I have my 1, and I move it 1, 2, 3, 4. So now I have 0.0001. So it's 0.0001. Okay. So which is the bigger number here? This one is top one. So this is a bigger number. This means that the concentration of hydrogen ions is greater in a pH of 2 than in a pH of 4. So that explains why it seems to be very backwards to you when you look at pH and the values of pH, the range. Okay, so we will stop there for today, and we'll continue on our discussion. We're going to move into organic chemistry soon. And I will see you all at 2 o'clock.